Welcome to the Drowsy Science Channel, and hello. Thank you very much for coming tonight. We travel into the core of the stars, the universe's powerful engines, tonight. These blazing balls of fire are not merely far-off spots of light. Some of them are so big they may engulf our solar system. Others crumble into minuscule fragments that rotate at hundreds of revolutions per second. And each of them is a forge, producing the components that comprise our world, our bodies, and everything we are familiar with. We are truly looking back in time as we gaze at the night sky. It's possible that the starlight that is visible to us tonight originated hundreds, thousands, or even millions of years ago. It's possible that some of those stars have already vanished, leaving only a faint trace of their presence. Others, however, will shine long after our world is gone. Please think about liking and subscribing if you like these calm excursions, or leave a comment with your ideas. One drowsy soul at a time, it guides others to this place as well. You don't have to do anything, though, for the time being. Just become comfortable. Reduce the pace of your breathing and let your mind relax a bit. Let's get started if you're prepared. Earth's orbit would be completely engulfed by the biggest stars currently known. It is impossible to imagine the sheer size of some stars. For instance, the radius of the red hypergiant UI is more than 1,700 times that of the Sun. Its outer surface would extend past Jupiter's orbit if it were positioned at the center of our solar system. The Earth's orbit would be totally engulfed by even smaller supergiants like Betelgeuse or Vi Canis Majoris supergiants. Compared to regular stars, which have a lifespan of billions of years, these huge stars are very uncommon, burning through their fuel quasars Onl Vi Canis Majoris rapidly and Vi Canis Majoris rapidly Andy existing for a few million years. Because of the instability of their enlarged atmospheres, material is released into space in the form of massive clouds that spread outward like smoke. These giants' huge size serves as a reminder that, despite being enormous by normal measures, our own Sun pales in comparison to the genuinely enormous suns that are dispersed throughout the cosmos. The heat from some stars can outshine entire galaxies. Some rare giants, known as Eta Carquasarapidly Andersini and hyperluminous stars, can emit more energy than the combined light of billions of suns, while the majority of stars shine with a familiar brilliance. The energy released by stars such as nebulequasars, a Lueta Carinae minus blue variable, is so great that it can compete with the brightness of entire tiny galaxies. Eta flared so furiously in the 19th century that it briefly surpassed all other stars in the night sky in brightness. This kind of star lives dangerously, burning hydrogen at incredible rates and frequently exploding as a supernova, while being located almost 7,000 light-years away. They are surrounded by brilliant nebula Nebueta Carinae, Laius, a result of their enormous light pushing forth so forcefully that it sweeps away their outer layers in tremendous winds. These dazzling lights serve as a reminder that even a single star has the power to briefly rule the universe. The remnants of stellar explosions are known as neutron stars. The core of a large star may collapse into an amazing object known as a neutron star when it dies as a supernova. Despite being only 20 kilometers across, these objects have more mass than the Sun. Atoms are compressed so much during the collapse that protons and electrons combine to form neutrons, producing stuff denser than anything else that is known to exist outside of black holes. Billions of tons would be contained in a single teaspoon of neutron star material. Their magnetic fields are unbelievably powerful, their surfaces are solid, and their gravity is enormous. Despite their small size, they radiate light or use their remaining energy to heat their surrounds. Nebulae surroundings. Each allows them to glow across the universe. The collapsing cores of once great suns have become whirling, dense remains known as neutron stars, which are stellar ghosts that cast doubt on our knowledge of matter. They demonstrate to us how far the universe can push the bounds of physics. Hundreds of times per second, pulsars rotate. Some neutron stars have even more startling characteristics. They are called pulsars, and they frequently revolve hundreds of times each second. As viewed from Earth, they produce a regular pulse by sweeping beams of light or radio waves across space with each revolution. The millisecond pulsars, which are the fastest pulsars, can spin more than 700 times per second, which is quicker than a kitchen blender's blades. Astronomers utilize these pulses as cosmic clocks since they are more accurate than atomic standards in terms of time. Before their actual nature was known, the discovery of pulsars in the late 1960s even sparked conjecture that they might represent communications from extraterrestrial civilizations. Pulsars are now utilized to test Einstein's theory of relativity's predictions, and even to look for gravitational waves that are reverberating throughout the cosmos. They are some of the universe's most dependable lighthouses. Surroundings, lighthouses. Atoms can be torn apart by the powerful magnetic fields seen in magnetars. The strongest known magnetic fields in the universe characterize magnetars, an unusual kind of neutron star. The strength of a magnetar's field can surpass that of Earth by 1,000 trillion times. It is nearly hard to understand such power. It would be sufficient to reorganize matter itself, break apart molecules, and warp atomic structures. Magnetars have the ability to produce massive flares when their magnetic fields abruptly change, releasing more energy in a split second than the Sun does over hundreds of thousands of years. These outbursts, which can occasionally momentarily outshine all of the stars in our galaxy combined, have been seen over great distances. Luckily, there aren't many magnetars lighthouses, magnetars, and none that are close enough to endanger Earth. They act as harsh laboratories in space, demonstrating to us what occurs when physics is stretched beyond what is possible to replicate on Earth. Some stars flatten into oblate forms due to their rapid rotation. Not every star is a flawless sphere. Centrifugal force causes a star's equator to bulge outward during exceptionally fast rotation, flattening the star into an oblate, magnetars, oblate, squashed shape. The star Ina is a well-known example, spinning so fast that its diameter at the equator is 50% more than its diameter from pole to pole. Material may be thrown into space by such fast spinning, creating gas disks around the star. Our perception of stars as round, balanced orbs is called into question by these warped suns. Rather, they demonstrate how spin, along with mass and age, can affect the dynamic and chaotic nature of star lifetimes. Compared to their slower revolving oblate, revolving siblings, stars that rotate more quickly may also mix their interior layers more efficiently, extending their lifespan. They glitter like any other star when viewed from a distance. However, up close, the unrelenting pull of their own speed is dramatically stretching them. Each year, hypergions can shed more mass than the Sun. Among the universe's most erratic and transient stars are hypergiants, revolving hypergiants. They have a price for their enormous size. Their outer layers are unable to remain attached because of how fiercely they burn through their fuel. Rather, they lost mass in strong stellar winds, surpassing the mass of the Sun in a matter of thousands of years. A massive nebula formed by material that surrounds Eta, one of the most well-known space hypergiants. Hypergiants, NDS, has fired into hypergiant I hypergiants T. Space surrounds, the ingredients that can potentially create new stars and planets, are added to the galaxy by these gas and dust storms. However, the technique is harmful to the supermassive hyperspace surround itself. It will most likely detonate in a powerful supernova, possibly even creating a black hole in the process. These stars demonstrate the extremes of what a star can be. They are cosmic firestorms that are both beautiful and devastating. Black holes have the ability to tear apart stars. A star will die violently if it approaches a black hole too closely. The star is stretched like chew by the black hole's tidal forces and the gravitational differential between its close and far sides. A tidal disruption event is a calamity that tears apart a star that veers too close. As it descends into the black hole, the star material forms a luminous disk as it spirals inward. An entire galaxy's worth of stars may momentarily be eclipsed by the light burst released by this process. Occasionally, material jets are hurled outward at almost the speed of light, dispersing the devastation throughout the cosmos. Although they are uncommon, these occurrences give astronomers a means of studying black holes that would otherwise be invisible. Every one of them is a cosmic drama, a bright star torn apart by gravity's ultimate power. Stars are torn apart in dazzling flashes by tidal disruption events. Astronomers may be observing the devastation of a star by a black hole when they notice abrupt, strong bursts of light at the centers of galaxies. When a star deviates from the black hole's gravitational pull and is stretched past recognition, these tidal disruption events take place. An accretion disk is formed by the star's material, which heats to millions of degrees and emits ultraviolet and X-ray light. As the black hole consumes its meal, these flares may continue for months or years before progressively fading away as the remaining stars disappear. By observing these occurrences, scientists may determine the masses of black holes and get insight into the evolution of galaxies. They also act as potent reminders that the underlying forces that form the cosmos can still affect even the biggest, brightest, and most resilient stars. Seeing one come to life is a glimpse of gravity's untamed, all-consuming desire. Gravitational waves can be produced when stars collide. One of the universe's most dramatic events can occur when two stars in a tight binary system collide after spiraling together. In particular, neutron star mergers emit energy in the form of ripples in space-time itself as well as light. Waves caused by gravity. These waves squeeze and stretch space as they move outward at the speed of light. Scientists discovered gravitational waves from one of these collisions in 2017, which were followed by visible light and gamma-ray bursts. For the first time, people saw light and gravitational waves from the same cosmic event. Additionally, these collisions create heavy elements like platinum and gold, which provide the universe with the building blocks for planets and life. Every gravitational wave ring that we can see is a signal from stars colliding inconceivably far away. Intergalactic space is where some stars are expelled. Not all stars are safe within their galaxy. Some are hurled so fast that they completely escape, floating by themselves into the immense blackness between galaxies. Violent occurrences like a close encounter with a death, a hypergiant supermassive black hole, or the chaotic disintegration of a star cluster can produce these rogue stars. After being expelled, they travel through the cosmos, bringing their planets, if any, into an unfathomable state of solitude. Imagine a single sun that has traveled for a very long time without a galaxy to call home, billions of years from its birthplace. Astronomers think there may be a vast number of intergalactic stars, like embers blown from a fire, but they are difficult to find. They serve as a reminder that even something as enormous as a star can become lost in the cosmic sea, and that space is dynamic and full of chance. It's possible that the initial stars were hundreds of times as massive as the Sun. The first stars were created in the early universe, before galaxies formed. They are known as the third stars by astronomers, and they were probably gigantic, hundreds of times more massive than our Sun. These giants grew quickly and burnt fiercely because they lacked heavy elements to temper the gas clouds they came from. On cosmic timescales, their lives might have lasted only a few million years. The first carbon, oxygen, and iron, the elements necessary for planets and life, were introduced into the cosmos when they died and burst into a massive supernova. The old chemical structures of the universe still bear the imprints of these primordial stars, even though none of them are alive today. Scientists are assembling the story of how the first light broke through the darkness and changed the universe from being made of empty hydrogen to being able to support life by examining those hints. black dwarfs will eventually form when white dwarfs cool. As stars like our Sun age, their outer layers fall away, leaving behind a white dwarf, which is a hot, dense core. Initially, the residual heat from their previous nuclear fires causes these remains to flash brightly. However, they gradually radiate that energy out over billions and trillions of years, fading into darkness. The term black dwarf refers to the last stage, a dead, chilly star that has lost its light. There aren't any yet, since even the oldest white dwarfs cannot cool that much since the cosmos is too young. Black dwarfs are a concept from the far future, when the universe will be a more subdued and gloomy place. They stand for the final fate of innumerable suns, a silent testament to the fact that time eventually overcomes even the brightest stars. When the last stars die, the universe might end in darkness. The universe's far future might involve a protracted plunge into darkness if it keeps expanding indefinitely. No new stars will form as the existing ones progressively run out of fuel. Even the slowest burners, red dwarfs, will eventually fade, even if they may shine for trillions of years. Planets will freeze, galaxies will become fainter, and the night sky will be devoid of stars. Only black holes and the dim remnants of dead stars remain in this picture, which is frequently referred to as heat death or supermassive death, as the universe grows quiet and frigid. Even if this future seems unthinkably distant, the idea is both sobering and oddly serene. The stars have a beginning and an end, and we are here while the sky is still illuminated by their light. Looking up now is to see a universe yet in its young, starry glory. According to certain hypotheses, future universes may produce new stars. Despite the possibility that our universe will eventually go dark, several theories contend that this is not the end of the story. Cosmological theories suggest that our world may bounce or create completely new universes. The cycle of stars may rekindle in those new beginnings. In order to maintain continuity throughout cosmic generations, the elements created in our universe may serve as the seeds for the next. Similar to how stars die and release the elements needed to produce new stars, universes may also go through a similar cycle of dissolution, rebirth, and renewal. This idea presents a vision in which starlight never really goes out, despite being incredibly speculative. Rather, it moves across scales that are beyond our comprehension. According to this perspective, the stars overhead are not merely a component of our cosmos, but rather of an endlessly recurring pattern, a dance of light and rebirth. For trillions of years, the tiniest stars can continue to burn. Stars don't all die young and live fast. The tiniest ones, known as red dwarfs, can last for trillions of years, much longer than the cosmos has been around, because they consume their fuel so slowly. These stars are frequently undetectable to the human eye from Earth because they are cooler and fainter than our Sun. Despite this, they are the most prevalent stars in the universe, accounting for most of the Milky Way's suns. Given their extended lifespans, red dwarfs may harbor planets where life has had time to develop and flourish over unthinkable time spans. The world itself is too young for any of them to have aged yet. This means that long after brighter stars like the Sun have gone, these little persistent embers will continue to light the night sky in the far future. Only dim red stars will be left after trillions of years. The biggest and brightest stars will burn away earliest as the universe ages. The lifespan of blue giants and hypergiants is barely a few million years. The Sun and other stars persist for billions of years. However, red dwarfs, tiny, effective stars, live for trillions of years. They will eventually take over as the universe's main light sources over very long timescales. A dim red light, a softer and lonelier, hypergiant lonelier sky, may be the only light emitted by the galaxies of the far future. Even these long-lived stars will eventually run out of fuel and turn into white dwarfs, which will eventually turn into black dwarfs. The cosmos will change from being a vast region illuminated by stars to one that is only illuminated by dying embers. In this cosmic twilight vision, the universe is carried into its closing chapters by the silent burning of its last stars. We currently dwell in its golden period, encircled by dazzling suns of many hues and sizes. Super-large black holes can be orbited by stars. Super-large black holes, which are millions to billions of times heavier than the Sun, are found at the centers of galaxies. Remarkably, stars are able to circle them directly, following routes that defy gravity. Astronomers have seen stars in our Milky Way circling the black hole at the center of our galaxy, Sagittarius, which is an asterisk. S2 is one such star that swings within a cosmic hair's breadth of the black hole at only 17 light hours. It travels at around 5,000 kilometers per second at its closest approach. By tracking these orbits, scientists are able to verify Einstein's theories regarding how gravity distorts space-time and measure the black hole's mass with remarkable accuracy. These stars reveal that the dance of starlight may continue even in the shadow of a black hole, surviving when we might expect them to be destroyed. Black holes can be sped away from by the quickest stars. A star doesn't necessarily die when it gets too close to a black hole. Sometimes the great gravity causes it to be thrown out at amazing speeds. With speeds of millions of kilometers per hour, these hypervelocity stars are capable of completely leaving their home galaxy. There are a number of these rogue stars in the Milky Way, hurtling out into intergalactic space. Their travels might have started close to the asterisk Sagittarius A, where interactions with the central black hole functioned as a slingshot. The outcome for any planets that would circle such a star would be remarkable. Speeding through the cosmic void by itself, a solar system was hypervelocity system was cast, ADR system wavesift to drift. These star exiles' discovery shows how dynamic galaxies can be and how black holes influence both what enters and what is thrown out. In reality, a large number of the stars you see represent numerous systems. A star frequently appears as a single point of light to the unaided eye. However, many are actually doubles, triples, or even bigger groups that are held together by gravity. With two suns around a similar center of mass, binary stars are particularly prevalent. While some pairings circle each other just once per thousands of years, others are so far apart that they interchange materials. A person on a planet orbiting such a system may see several shadows cast by the rising and setting of 2 or 3 suns in the sky. Alpha Centauri, or Cadre Centauri, our nearest star neighbor and a triple system, is a well-known example. Astronomers can learn more about the formation and evolution of stars by examining these pairings and groupings. What appears to be a single star in the night sky is frequently a clandestine family dancing gracefully and for a long time. New stars can emerge when an existing one dies. When a large star dies in a supernova, it changes its surroundings rather than simply vanishing. Shock waves from the explosion compress the surrounding gas and dust clouds and cause additional waves of star formation. Thus, the demise of one star might trigger the emergence of numerous others. Such an event, with its nebula enhanced by heavy materials spread by a previous generation of giants, might have given birth to our own supernova Centauri sun. By continuously recycling stuff into new forms, these cycles guarantee that galaxies stay fruitful with starlight. When a bright star dies, it leaves behind more than just ashes. The seeds of future planets, suns, and possibly even life itself are left behind. Stars don't just die. By passing the torch, they start the next chapters in the universe's continuous story. In rare supernova rebounds, some stars explode more than once. Some stars defy expectations, but the majority of supernova explosions end in finality. A big star may erupt violently, survive the blast, and then explode again years or decades later in incredibly rare instances. Pulsational parentability, Sagansun. The name supernovae is given to these anomalous occurrences. The star ejects massive amounts of mass, becomes unstable, stabilizes momentarily, and then collapses permanently. Because of their unpredictable brightness, these stars can produce several strong outbursts, leading astronomers to believe they are seeing repeated supernovas in the same location. These unusual stellar deaths show how different huge star outcomes can be and how much we still don't know about the boundaries of instability and nuclear fusion. They are stars that, from a cosmic perspective, appear unable to let go, leaving behind a striking, flickering record of their battle against gravity's last tug. Supernovae of type Ea aid in the measurement of the universe's size. A unique class of exploding stars known as type Eaa supernovae shine very consistently. A runaway thermonuclear explosion is the result of a white dwarf star in a binary system accumulating too much stuff from its companion. The peak brightness of these explosions is almost constant across the cosmos because they always occur at around the same critical mass. Astronomers can use them as dependable beacons to determine cosmic distances since they are standard candles. Scientists can determine how far away they must be by comparing their apparent brightness from Earth with their actual brightness. One of the greatest discoveries in astronomy, the accelerated expansion of the universe due to dark energy, was made possible in large part by Type A supernovae. In addition to being breathtaking stellar deaths, they serve as essential benchmarks that enable us to understand the vastness of the universe. Heavy elements are dispersed around the galaxy by supernovas. The heart of a star is where all of the gold, silver, iron, and calcium atoms on Earth were formed. Those heavy elements are blasted into space by huge stars that explode as supernovae, enriching the interstellar medium. That material eventually forms new planets, stars, and life forms. The universe would be considerably simpler and primarily composed of hydrogen and helium if supernovas didn't exist. Rather, complexity is sown with each burst. Once in such a blast, the calcium in your bones and the iron in your blood were carried outside and drifted across space before arriving on Earth. The elements of life are dispersed widely by supernovas, which are both violent finishes and beginnings. Stars ensure that the universe is rich and varied in addition to being full of light by acting as both creators and destroyers. Literally, you are composed of stardust. Despite its beautiful sound, this is a scientific fact. Your body's atoms were formed in stars. Supernovas and star cores produce the iron in your blood, the carbon that makes up your cells, and the oxygen you breathe. Those components were floating in space, waiting for an opportunity to unite, billions of years before Earth was ever a thing. Carl Tipp, Sagan Famo's Supernovae, insouciantly remarked, "We are made of star stuff." This statement encapsulates a basic truth. All trees, all people, and all stones are made of recycled stardust. You are seeing more than simply far-off suns as you gaze up at the night sky. You're witnessing your own beginnings. The raw elements came from the heavens. Consequently, we are the universe's self-awareness. There is a direct, physical, and very humble connection between us and the stars. Iron denotes the point at which a star can no longer be powered by fusion. Nuclear fusion, which is the process of combining lighter elements into heavier ones, is what gives stars their brightness. Energy is released during this process, but only to a certain extent. The equilibrium shifts when silicon starts to fuse into iron in a star's core. When iron is fused, no energy is released. It absorbs it instead. This implies that fusion can no longer sustain a star against gravity once iron builds up in the center of the star. Collapse then becomes unavoidable, resulting in a devastating implosion and frequently a supernova. For large stars, the presence of iron is a death sentence, signaling the basic depletion of their fuel. It's amazing that this common metal, which we are so accustomed to on Earth, serves as the cosmic tipping point that determines the timing of the collapse of giants of light. Stars use outward pressure from fusion to balance gravity. A precise balance between two opposing forces holds a star together. Its entire bulk is drawn inward by gravity, which attempts to compress it into a dense core. Heat and radiation are pushed outward by fusion, which is the central burning of hydrogen into helium. The star is stable as long as these two forces are balanced. If the pressure is too high, it will inflate. If it is too low, it will compress. For billions of years, our Sun has kept this balance, and it will do so for billions more. However, the balance will sag and tip, and the Sun will change into something quite different when the fuel at its core inevitably runs out. The basic reason stars continue to exist as constant sources of light instead of abruptly disintegrating or blowing themselves to pieces is because of this tug of struggle. Stars would instantly collapse in the absence of fusion. Stars are not the only things that shine because of fusion. They are kept from imploding by it. Gravity would quickly crush a star into a dense, collapsed state if fusion didn't provide an external push of energy. Every second, even the soft golden radiance of our Sun is balanced on this knife edge. It is prevented from collapsing under the weight of its own enormous mass by the continuous fusion of hydrogen into helium. With amazing forces at work, this balancing act is much more difficult for larger stars. Gravity always prevails when fusion comes to an end, dragging the star into a black hole, neutron star, or white dwarf. As long as fusion persists, stars will continue to exist. Their brightness is a tenuous triumph over gravity's inexorable pull inward. Compared to the Sun, some stars burn fuel 1,000,000 times quicker. Our Sun is patient, but not all stars are. The largest ones use up to 1,000,000 times the speed at which they burn their nuclear fuel. This indicates that even while they are considerably bigger and stronger, they only have very brief lifespans, sometimes just a few million years. The Sun, on the other hand, will continue to shine for about 10 billion years. Blue light blazes from these rapidly burning giants, which release energy into space and use star winds and radiation to shape their galaxies. Their brief lives terminate violently, frequently in supernovae that release heavy materials into the universe. The way that size determines fate is demonstrated by the contrast between them and stars like our Sun. A star's life is shorter and more dramatic the larger it is. They are spectacular but short-lived cosmic fireworks. The Sun will eventually grow into a red giant, but smaller stars will continue to exist as stable candles into deep time. Despite being stable right now, our own Sun has a bright future. It will run out of hydrogen in its core in roughly 5 billion years. The equilibrium within will shift as fusion turns to helium, causing the Sun to massively enlarge into a red giant. Its surface will spread outward, possibly swallowing up Earth as well as Venus and Mercury. The Sun's core will compress and heat up, while its outer layers will shine a faint red that is far colder than the golden brightness of today. The center will eventually contract into a white orb, while the surrounding layers will eventually float away into space to become a bright planetary nebula. Even while this change is far off, it serves as a reminder that even stars like our Sun are transient, following paths determined by gravity and fusion physics. Eventually, our well-known star will change completely. Sirius is the brightest star in the sky. Sirius rules the skies on a clear night. It shines almost twice as brightly as Canopus, the next brightest star, and is also known as the dog star. Canopus, the dog star. Its inherent luminosity contributes to some of its brilliance, but from Earth, it seems brilliant due to its close proximity. Just 8.5 light dog star. Dog star, light years. For thousands of years, ancient societies observed Sirius and associated it with myth, calendars, and navigation. When it rose in the morning sky in ancient Egypt, It signaled that the Nile would flood. Astronomers now understand that Sirius is a binary system. Sirius B, a faint but dense white dwarf that was originally a huge star itself, and Sirius A, a brilliant hot white star. They appear to be one sharp point of light to the unaided eye. In addition to being bright, Sirius serves as a reminder that the night sky's outward looks frequently conceal more complex meanings. The names of some stars are thousands of years old. The brightest stars that mankind could see were given names long before telescopes were invented. These names had connotations related to myth, agriculture, or navigation. While Vega and Alta have ancient Arabic and Latin origins, stars like Betelgeuse, Rael, and Aldebaran have Arabic ancestry. Stories about stars were used to help civilizations in China, India, Greece, and Egypt make sense of the sky. Individuals' archaic names still exist now, linking us to individuals who gazed at the same sky thousands of years ago. Every well-known constellation has a name that has been passed down through languages and cultures, creating a tapestry of human history. The old names still reverberate through time, even though astronomers now use catalog numbers for accuracy. They serve as a reminder that we have a connection to the stars beyond science. It has a rich cultural heritage that dates back to the dawn of civilization. To navigate the oceans, ancient nations relied on stars. The stars were trustworthy guides before GPS and compasses. Polynesian explorers navigated their boats over thousands of kilometers of open ocean by learning the rising and setting times of the stars. In the Northern Hemisphere, people have traditionally used the North Star, which is nearly fixed in the sky, to determine latitude. The sky map served as a navigational aid for Viking explorers, Greek mariners, and Arab commerce. Even seasonal animal and human migrations were frequently synchronized with the stars. These abilities were transmitted verbally through stories and songs that encoded whole star charts. It took exceptional memory and observational skills to navigate by the stars. However, it was successful. Humans relied on starlight to securely transport people to new places long before technology. Though we now gaze upon them in awe rather than necessity, the same stars still shine above us today. Over time, the North Star undergoes modifications. As the North Star, Polaris is well known for appearing to be still as the other stars revolve around it. However, it hasn't always played this precise, individual part, and it won't always. In a cycle of roughly 26,000 years, the Earth's axis wobbles slowly. This motion is known as a precession. This indicates a slow shift of the pole star, a round precession. A star around 3000 B. True north was indicated by the star Thuban in the Draco constellation in CE. The brilliant star Vega will replace it in around 12,000 years. Alaris is merely the most recent installment in a lengthy tale of changing sky. The several stars that formerly held the Northern Crown were aligned with ancient constructions such as stone circles and some pyramids. It's like witnessing the Earth breathe over millennia as you watch the pole star move. A reminder that everything is constantly changing, including the patterns we rely on in the sky. Compared to other worlds, our sky appears different. You know, the constellations would disappear if you were standing on a far-off planet. From Earth, stars only appear clustered together due to our unique perspective. Their configurations would distort into strange shapes when viewed from light years away. Our Sun would be a dim extra star in the sky on a planet orbiting Proxima Centauri, Installment Centauri. From Andromeda, the Milky Way would appear as a bright ribbon, and the familiar stars would be obscured by its whirl. This change in viewpoint demonstrates that constellations are deceptive representations of angle and distance. The night sky is a three-dimensional ocean of suns that appears differently from each shore, rather than a static image. Imagining different skies makes us aware of how much our perspective of the cosmos is influenced by our position within it. The constellations of the future will be completely different. The Big Dipper, Cassiopeia, and Centauri. Cassiopeia, Orion, and other familiar constellations are transient. Stars move in relation to one another as they wander across space over hundreds and millions of years. The recognizable patterns will gradually become unrecognizable. It's possible that the Dipper, Cassiopeia, will lose its handle, the Hunter Orion will lose his belt, and completely new groups will form. These changes seem too gradual for us to observe in a lifetime. However, the sky is always changing on a cosmic scale. Future species, or possibly civilizations, will inherit skies full of various maps. Just as our constellations are associated with past cultures, theirs will have a mythology that is specific to their time. Tonight's constellations serve as a reminder that nothing in the universe, not even the patterns we make of the stars, is permanent. They are pictures of a transient arrangement. Gravitational lensing can distort the light from stars. Light is bent by gravity, as Einstein predicted, and it was verified a century ago. The light from a far-off star may be distorted and magnified when it approaches a huge object like a galaxy or black hole. We refer to this predicted phenomenon as gravitational lensing. It can occasionally cause a star's light to look much brighter than it actually is, or split into many pictures. Even individual stars have been seen by astronomers magnified in this manner, appearing momentarily over billions of light years. Detecting those stars would be impossible without lensing. We can see farther into the cosmos thanks to nature's magnifying glass than we could with only our tools. It demonstrates that space is not empty, but rather malleable, allowing light to bend in unexpected directions and uncover hidden gems. The invisible hand of gravity even shapes the trajectory of starlight. There will be constellations that vanish in the far future. Culturally constructed, constellations are designs drawn on top of the starry sky. However, they are not permanent. Some of today's most familiar forms will disappear as stars drift and the Milky Way rotates. Orion will no longer have its recognizable shape, with its brilliant stars dispersing throughout the sky after roughly 50,000 years. The Big Dipper won't resemble a dipper at all after a few million years. These constellations might not be identifiable to viewers in the future. Future beings will inherit their own sky, just as ancient humans saw different skies than we do. Our phenomenon. Our mythologies are connected to a fleeting arrangement of stars, and the constellations we are familiar with are only transient alignments. They serve as a reminder that the sky itself has a past, and that our maps of it will eventually become as antiquated as the old sea charts. Over millennia, star positions gradually change. Stars seem fixed, although they are in motion all the time. The motion is almost undetectable to the human eye due to their great distances. However, the changes accumulate over centuries and millennia. We refer to this slow drift as appropriate motion. Every few decades, the Barnard star, for instance, changes dramatically against the background, the quickest proper motion of any star in the sky that is currently known. The steady shuffling of the skies can be seen when comparing ancient and contemporary star maps. Over the course of human history, even constellation shapes have undergone subtle changes. We are reminded that what appears to be eternal is not by this changing sky. On the dome, the stars are not painted dots. They are suns with unique journeys and tails as they move through the galaxy. Lines of motion across cosmic time are traced by their light. The stars that surrounded the sun used to be different. No. Our sun is not stationary either. Every 200 million years, it completes one orbit around the Milky Way's center. Its neighborhood shifts throughout time. Today's nearby stars will fade away to be replaced by new ones that span our galaxy. The closest neighbors of the sun were completely different in the distant past. In another sky, their light mixed with ours. The stars we recognize will disappear from view as it continues its journey, and the constellations surrounding us will change. This cosmic motion demonstrates that even the position of our sun is transient, as it is a component of a larger revolution that carries us throughout the galaxy. Looking into the sky is like looking at a single frame of an infinite voyage through the aeons when our star friends come and go. Some of the universe's earliest stars are found in globular clusters. Dense, spherical swarms of stars, frequently numbering in the hundreds of thousands, are known as globular clusters. Like glistening satellites, they circle the periphery of galaxies. They are all remnants of the early cosmos. Nearly as old as the cosmos itself, several of the Milky Way's globular clusters are over 12 billion years old, while enormous stars are burnt away aeons ago. Their stars are often long-lived giants and small, dim red dwarfs. A globular cluster appears as a brilliant snowball of light when viewed through a telescope, with stars crammed together so densely in the center that they blend together. The beauty of these clusters is exceptional. They provide us with windows into the past, revealing the formation and existence of the first stars. Studying them is similar to reading a book about the early history of our galaxy that was written in starlight. The Milky Way contains some very old stars that are almost as old as the cosmos. A few elder stars, ancient suns that have existed from the beginning of time, are concealed among our galaxy's younger star generations. Some are almost as old as the cosmos itself, dating back more than 13 billion years. Very few heavy metals were present in the primordial gas that gave rise to these stars. By examining their spectra, the fingerprints of the atoms in their light, and identifying signatures that have hardly changed since the Big Bang, astronomers are able to identify them. Although these old stars are uncommon, they provide information on the early stages of star formation, before galaxies developed and the universe was populated by heavy elements. To stare upon one is to peer into the past, to establish a connection with a survivor from a period when the cosmos was young and dark. The first stars are burnt areas just starting to twinkle. The galaxies from which stars are created can outlive them. Galaxies are dynamic. Gravitational forces can cause them to collide, merge, or even tear apart. However, the stars inside them have the ability to endure these changes. After a galactic merger, a star that was born in a tiny galaxy may be swept into a larger one and continue to shine for billions of years. Even after their home galaxy has disintegrated, some stars might be launched into cosmic space and left to fend for themselves. This allows stars to endure when the structures that gave rise to them are destroyed. It serves as a reminder that stars persist long after galactic boundaries change and are both independent entities and products of galaxies. These lone survivors are cosmic witnesses who are experiencing chaos on a scale that is nearly unthinkable. The cradles that first kindled them were outlived by their light. Some stars have enigmatic gas shells surrounding them. Not every star shines alone. During unstable times, some are covered in odd shells of dust and gas that are thrown from their surfaces. The radiation from the stars can cause these shells to create luminous arcs, rings, or bubbles. The causes differ. Strong stellar winds cause some stars to lose mass, while outbursts cause others to momentarily enlarge and lose their outer layers. The debris frequently joins complex nebulae to form stunning and perhaps perplexing designs. Astronomers may occasionally observe several shells, indicating that a star has had recurrent periods of shedding. Not only do these gas shells adorn the stars, they add elements to the galaxy that will eventually create new planets and stars. Studying them is like watching a star alter mid-transformation while donning dazzling veils that conceal its past. Myrrh is shed by Wolf-Rayet stars in strong winds. Massive, uncommon, and extremely unstable are Wolf-Rayet stars. Their outer layers are blasted away by intense stellar winds due to their intense and bright burning. Every year, these winds have the capacity to remove over 10 Earth masses of material, encircling the star with striking gas and dust halos. Their exposed cores, which frequently reach temperatures beyond 50,000 degrees Celsius, Wolf-Rayet stars, shine with intense heat. Wolf-Rayet stars, which have brief, violent lifetimes before exploding as supernovae or falling into black holes, are thought to be at a transitional stage. They contribute significantly to the enrichment of galaxies with heavy metals, despite their rarity. The raw materials for new worlds are scattered by their raging winds and eventual explosions. They are stars living on the edge, blazing brilliantly before their certain demise, scorching so fiercely that they cannot endure for very long. Like boats on water, some stars produce bow shocks. High-speed space travel can cause a star to smash into nearby gas and dust, producing a bow-shaped shockwave in front of it that resembles the wake of a boat in water. Astronomers may see these bow shocks as arcs or crescents in front of the star because they glow in infrared light. They show the density of the medium the star is traveling through as well as its speed. These stars are frequently runaways, expelled from their birthplaces by gravitational collisions or explosions. As the star travels through areas rich in gas, the supernova's luminous protostar's wake is short-lived. In space, every bow shock resembles a frozen wave. A star's restless trip throughout the cosmos is marked by a bright footprint. Runaway stars travel at amazing speeds across space. Not every star stays bound to the place where they were born. At up to hundreds of kilometers per second, some are expelled from their clusters or galaxies. Close interactions with large black holes or supernova explosions that kick them away can both launch these runaway stars. In severe situations, they reach hypervelocity, which allows them to completely leave their galaxy. The outcome for any planet circling such a star would be remarkable. A solar system launched into the cosmos by itself. Even though they are uncommon, runaway stars demonstrate the chaotic side of the universe where violent forces have the ability to abruptly upend stellar existence. Like cosmic exiles, they dart throughout the galaxy, a reminder that gravity's antics may be unpredictable, even for stars. Dust frequently obscures the youngest stars. Rarely do newborn stars come into their own immediately. Thick clouds of gas and dust, the remains of the material that collapsed to produce them, are where they are born. Ordinary telescopes cannot see the stars because of these dusty cocoons that obstruct visible light. Rather, by looking through the veil using radio and infrared data, astronomers can see clusters of protostars that are still gaining mass. These young stars are frequently encircled by disks of material that could eventually develop into planets. The dust is eventually removed by radiation and stellar winds, allowing the stars to shine brightly. Seeing a nascent star in action is like watching creation unfold. Only a small portion of a star's life is spent in this uncommon and fragile stage. Before nuclear fusion even starts, protostar wakes are, and protostars glow. Fusion is not instantly ignited when a star first forms. Prior to that, it is a protostar, a dense mass of gas that is falling apart due to gravity. The surrounding protostars glow softly from gravitational energy alone as it shrinks, the center heating up. The star acquires material from its surroundings throughout this stage, which can span hundreds of thousands of years, making it bigger and more massive. Its presence in the dark clouds where it originates is indicated by the frequent stream of gas jets from its poles. The protostar's surroundings don't formally become a star until its core temperature hits around 10 million degrees Celsius, at which point hydrogen fusion starts. When a sun's destiny is still being pieced together from darkness, this concealed phase is the universe's silent prelude to starlight. The distinction between stars and planets is muddled by brown dwarfs. Not everything in space perfectly fits the description of a planet or star. Between the two, the twilight zone is home to brown dwarfs. They glow dimly with residual heat from their formation, too large to be named planets, but not massive enough to maintain constant hydrogen fusion like genuine stars. Some turn into dull, chilly objects after temporarily fusing deuterium, a heavy type of hydrogen. Because they mostly shine in infrared light, brown dwarfs can be difficult to see. However, several of them have been discovered by astronomers orbiting stars or wandering alone. They challenge our classifications by showcasing the variety of items the universe is capable of producing. In a way, they resemble failed stars or possibly overgrown planets, serving as a reminder that the universe frequently defies easy classification. Even bigger suns can be created by star mergers. Not all stars are alone. Two orbits can spiral together and merge if they are sufficiently close to one another. Massive energy is released during such collisions, occasionally resulting in spectacular galactic-Wydian spectacular eruptions. New layers of nuclear fusion ignite in the centers of the merging stars, making them frequently bigger, hotter, and more unstable. Certain mergers may even produce uncommon star types, such as blue stragglers, that would not otherwise form normally. Stars that have been rejuvenated by combining, giving them an extraordinarily youthful appearance. Additionally, disks of material left over from these explosions may scatter into space or form new planets. Violent stellar mergers remind us that stars' lives are not isolated but rather interconnected, impacted by neighbors and random contacts, even though they are a natural part of the cosmic cycle and transform them into new forms. It is possible for binary stars to steal mass from each other. One star grows at the expense of its companion in many binary systems. Gravity can cause stars' outer layers to spill over onto one another as they get older and become giants. The fates of both stars could be drastically changed by this mass transfer. The donor gets stripped to its core, occasionally leaving behind a white dwarf, while the receiving star may become hotter and brighter. In severe circumstances, the stolen material may cause a star to go beyond its stability threshold, resulting in a nova or perhaps a supernova. Some of the most spectacular sky occurrences are produced by these interactions, from strong explosions to changeable stars that flicker. Cosmic robbers and victims are binary stars. Their lives were intertwined in relationships as intricate and dramatic as any myth, albeit one that was enacted over millions of years in the midst of light and fire. Odd orbital paths can be produced by triple star systems. Not all stars are found in pairs. In delicate gravitational dances, they form trios and circle. There are various ways that triple star systems might organize themselves. A third star orbits farther away from the first two, or all three are bound in intricate shifting patterns. Any planets orbiting these systems may experience chaotic gravitational forces that affect their velocity. Planets can occasionally find themselves on extremely skewed orbits where several suns rise and set. The universe likes variety, as seen by the comparatively high frequency of triple systems. Looking at one via a telescope is like looking at a separate solar system from our own, where the cycles of day and night are completely different. These stars demonstrate that the typical solar system in which we dwell is only one of countless bizarre cosmic configurations. Multiple stars can be orbited simultaneously by planets. Although astronomy verifies that two suns are real, science fiction frequently depicts worlds with such a feature. Planets can follow stable orbits around double stars that circle both suns at the same time. The globe would undergo intricate day-night to day-night cycles with twin sunsets and changing light patterns in such systems. In a binary, other planets revolve around a single star, while the companion star rises and sets like an exceptionally bright moon. The existence of these unusual configurations has been confirmed by NASA's discovery of multiple such circumnavigatory planets using the Kepler spacecraft. Under several suns, life would be formed by cycles that are not found on Earth. Variations in light levels, seasons, and even shadows could cause unpredictable behavior. These systems remind us that the diversity of planetary ecosystems is more than we previously thought, broadening our perspective on what is conceivable. Hundreds of thousands of suns can be found in star clusters. Not every star is dispersed equally among galaxies. Some people are born in big groupings. In a comparatively tiny area of space, star clusters can contain hundreds of thousands of suns. For instance, stars at the centers of globular clusters may be just a few light years apart due to their extreme density. Stars regularly interact in these settings, trading partners or upsetting planetary systems. Younger and looser, open clusters are frequently adorned with hot, brilliant blue stars, which emphasize the group's youth due to their brief lifespan. A cluster is a population of stars blazing together when viewed through a telescope. A reminder that many suns are born in crowded star nurseries, rather than in isolation. Clusters gradually break up as their members go to join the rest of the galaxy. There are clusters that date back billions of years. Globular clusters persist for several 100 million years, whereas open clusters disintegrate. They are almost as old as the Milky Way itself, with several being over 10 billion years old. Gravity holds their hundreds of thousands of stars firmly together, giving them a dense structure that contributes to their lifetime. While faint red dwarfs continue to shine constantly, the brightest stars die over aeons, leaving behind red giants and dense remains. Like remnants, these clusters circle the galaxy. They were survivors of the Milky Way's early formation. By examining them, we can learn more about the chemical composition of old stars and the conditions under which galaxies were formed. They are cosmic time capsules that hold knowledge about a bygone era. Observing a globular cluster is similar to looking back at almost the whole universe's history. Clusters that are open gradually fade into the galaxy. In contrast to their spherical counterparts, open clusters are very brittle. They frequently originate in large stellar nurseries as clusters of dozens to thousands of newborn stars. They progressively separate over hundreds of millions of years due to gravitational pulls from the galaxy. The stars eventually merge with the rest of the population by dispersing into the galactic disk. About 4.5 billion years ago, our own sun is believed to have evolved in an open cluster that has since dissipated. Open clusters offer a glimpse of stellar youth, albeit brief, with hot, massive stars that cast dazzling colors on the surrounding gas. They demonstrate that stars are not created alone, but rather as siblings and temporary companions before separating to face their own destiny in the cosmos. Starburst galaxies have a rapid rate of star formation. Some galaxies have dramatic outbursts of star formation known as starbursts, day-night starbursts, or other galaxies, while galaxies such as the Milky Way create stars steadily. Stars are born in these conditions at up to 1,000 times the normal rate. Clusters of newborns light up entire regions. Light poured out like cosmic pyrotechnics as they united. When massive amounts of gas are compressed into new stars by tidal forces during galactic collisions, starbursts can result. Despite being magnificent, these phases barely span tens of millions of years on a cosmic scale. The starburst eventually fades as the galaxy runs out of gas. We can see from these galaxies that the rhythms of the universe can vary greatly. Always creative, sometimes serene, sometimes explosive. They serve as a reminder that galaxies are dynamic, ever-evolving systems rather than static groupings of stars. It is possible for stellar nurseries to span hundreds of light years, way years. Giant molecular clouds, which are enormous stores of gas and dust that can extend for hundreds of light years, are where stars are created. Material in these areas is gradually drawn by gravity into clusters, which eventually collapse into protostars. These nurseries are seen through telescopes as bright nebulae, where nascent stars gleam against the clouds that gave birth to them. One of the closest instances is the Orion Nebula, which is visible even with the unaided eye, brimming with enormous blazing stars that illuminated their surroundings. Whole generations of stars can grow together inside these nurseries, forming clusters that eventually disperse. Observing a star nursery is like witnessing the act of creation. The years, the universe's basic components coming together to form suns that could eventually illuminate planets and even life. These clouds are the wombs of the universe, forming galaxies' future skies. Jets are frequently blasted into space by young stars. Many young stars release narrow jets of material from their poles when they form from collapsing gas. For light years, these star jets can pierce the surrounding clouds, leaving behind glowing trails. By directing surplus energy outward, while the remaining gas sinks inside, the process is believed to help control how the star accumulates material. These jets are visible through strong telescopes as fragile filaments that glow in pinks and blues when they clash with neighboring gas and are illuminated by shock waves. Herbig Haro. The Haro objects are some of the most stunning astronomical views, bright indicators of exceptional youth. They represent the drama of starbirth, a brief but remarkable stage before the star settles into long-term stability, even though they only last a few tens of thousands of years. Cosmic heartbeats cause some stars to pulse in brightness. Some stars don't have constant illumination. Rather, they brighten and dim in a rhythmic pulse. Changes in the temperature and pressure of their outer layers cause these pulsing variable stars to expand and shrink in cycles. Some, such as Cepheid variables, have periods that are closely related to their inherent brightness and are so regular that they function as cosmic clocks. Astronomers can determine their actual luminosity and utilize their pulses as markers of distance throughout the cosmos by measuring them. Others, such as RR Lyrae and Cepheid Lyrae stars, have a similar function in mapping the galaxy, but pulse more quickly. These stars may seem to glimmer strangely to the unaided eye, but upon close inspection, their beating hearts become visible. Their consistent beats reverberate throughout space, transforming stars into organic timepieces and assisting us in mapping the immensity of the universe. Compared to blue flames, white stars burn hotter. We frequently consider fire to be the hottest thing in the world. However, even our fiercest flames are outshone by stars. Compared to the bluish flame of burning gas on Earth, white stars like Sirius A radiate at temperatures of 10,000 degrees Celsius or higher. To our eyes, their surfaces seem dazzling white or blue-white due to the extreme blazing that causes them to produce light throughout a wide spectrum. These stars use their hydrogen fuel more quickly because they are typically younger and more massive than the Sun. They are easily recognizable in the night sky due to their brightness. However, their lives are not as long as those of colder stars. We are experiencing energy on a scale well beyond earthly fire when we see a white star blazing down on us. Even the idea of flames looks insignificant in comparison to the heat of a fusion furnace. Among the biggest and coolest stars are red supergiants and white supergiants. White supergiants, red supergiants. Pregiants are remarkably cool by stellar standards, despite their scorching appearance. Their surfaces can only reach 3,000 degrees Celsius, which is lower than the 6,000 degrees Celsius of our Sun. However, their immensity compensates for their lack of warmth. Betelgeuse and other stars can grow to hundreds or even thousands of times the Sun's radius. They ejected their enormous atmospheres into space. Betelgeuse would go beyond Mars' orbit if it were at the center of our solar system. The lives of these celebrities are coming to an end, swollen giants getting ready to explode as a supernova. Both greatness and fragility are indicated by their red glow in the night sky. Their final fate as some of the universe's most magnificent stellar explosions is shaped by their intense internal burning despite their colder exterior. The Sun and other yellow stars are actually rather common. To us, our Sun feels essential and special. On a cosmic scale, however, it is just a typical middleweight star. It burns continuously and is categorized as a yellow dwarf, or GTP, main sequence star. It is neither particularly large nor faint. The Milky Way is dotted with billions of stars, each of which has the capacity to support planets. The Sun's gift is its ordinariness. Not too big that it burns out too soon, yet big enough to start fusion for billions of years. It gives life a permanent, stable place to start and grow. Knowing that our Sun is not unique is reassuring when we gaze up at the stars. If there is life in the galaxy, it might orbit a star that is similar to ours. Dependable, golden, and steadfast. In this instance, the commonplace might be just what makes it special. Red dwarfs are the most prevalent stars in the universe. Red dwarfs are by far the most prevalent stars in the cosmos, despite their faintness and difficulty being seen with the naked eye. They may comprise 3/4 of all stars in the Milky Way and are small, cool, and effective. Despite their abundance, none can be seen from Earth without telescopes due to their supergiant size and faint red light. Red dwarfs exist for billions of years, which is a lot longer than the universe's present age, because they consume their hydrogen so slowly. Because of their lifespan, planets near them would have plenty of time to support life, making them intriguing possibilities to host habitable worlds. They are the silent workhorses of the universe, considerably more numerous than the dazzling blue giants that catch our eye. These small, persistent suns are the main threads of the galaxy's brilliant fabric. The largest blue giants are the rarest stars. Blue giants are at the other extreme of the spectrum from red dwarfs. The Sun is dozens of times as large as stars. They evaporate in the blink of a cosmic eye due to their intense burning, which shortens their existence to a few million years. This shortness makes them unique. Only a handful remain distributed throughout the galaxy at any given time, despite the fact that many may form and then swiftly perish. They are incredibly bright when living and can frequently be seen for great distances. Their UV rays ionize gas clouds, create bubbles in the interstellar medium, and sculpt vast regions of space. The universe's pyrotechnics are these stars, extraordinary, fleeting, and unavoidable. A blue giant is a rare and ephemeral phenomenon that will soon collapse in one of the most spectacular deaths imaginable. The colors of stars are hardly visible to the human eye. Not all stars are white or yellow. Depending on the surface temperature, their light can range in color from deep crimson to frigid blue. Some stars emit light in hues so faint that they are invisible to the naked eye. Although they may all seem bluish or colorless to humans, their colors are revealed by scientific instruments. While colder stars light in the infrared, which is invisible without specialized sensors, ultraviolet stars burn with energy that is a phenomenon invisible to the human eye. By utilizing spectroscopy to separate starlight into rainbows that show its temperature, composition, and velocity, astronomers were able to observe these colors. The night sky is actually far more colorful than it appears, with hues that are just out of our range of vision. The stars we can see are but a small sample of a far more diverse palette that is burning brightly throughout the cosmos in all forms of light, hidden from our view. The color of a star indicates its temperature. Color is more than just ornamentation, it's a start-stop thermometer. The surface of a bluer star is hotter. Red dwarfs flare at a few thousand degrees, whereas blue giants can burn at tens of thousands. In between are yellow stars like our Sun. By examining the light from stars, astronomers can determine their temperatures thanks to a relationship called Wien's law. Filter-equipped telescopes can measure color balance and provide accurate data. The composition, speed, and age of a star can also be inferred from the rainbow spread of its light. Heat is directly translated into hue, and each star tells a narrative through its color. You are looking at a thermometer inscribed in starlight, a cosmic code that astronomers have learnt to interpret. Keep this in mind the next time you notice a faint red glow or a brilliant white dazzle. Low-mass stars efficiently and gently burn fuel. The smallest stars have the longest lifespans, and they range widely in mass. Slowly consuming hydrogen, low-mass stars efficiently transform it into helium. These tiny suns can light for trillions of years without running out of fuel, in contrast to big stars that burn through their fuel in a matter of millions of years. They are dark and frequently invisible to the human eye from Earth due to their lower temperatures. Nonetheless, they control the galaxy's stellar population. It is rare for these stars to die in spectacular explosions. Rather, they silently pass away as they gradually fade into white dwarfs. They are intriguing targets in the hunt for habitable planets because of their stability and durability. Low mass stars are the patient stewards of time, shining long after brighter stars have gone out, despite their lackluster luminosity. Stars are used to forge heavier elements like carbon and oxygen. Only the most basic elements, hydrogen, helium, and minuscule amounts of lithium, were present in the universe at first. Stars produced everything heavier, including carbon, oxygen, nitrogen, silicon, iron, and more. Atom by atom, the chemistry of life is created in their cores by nuclear fusion, which joins lighter atoms into heavier ones. These elements are sent into space by dying stars, where they are then absorbed by new stars, planets, and living things. Billions of years ago, in star furnaces, the carbon in your cells and the oxygen in your lungs were created. There wouldn't be any rocks, oceans, or DNA if stars didn't exist. The signature of a star that existed and perished before us is present in every atom heavier than helium. Reading the history of starlight etched into the composition of all things is what it means to study the periodic table. Some stars make it through close calls with black holes. The encounter between a star and a black hole can be catastrophic. It is stretched by tidal pressures, and the star is frequently ripped apart. But occasionally, the star makes it through despite all the odds. Only a portion of the star's outer layers are removed by the black hole during these grazing interactions. What's left keeps circling, damaged but undamaged, frequently left deformed or unsteady. Because they bear the scars of near destruction and continue to shine, astronomers refer to these survivors as zombie stars. More material may be removed with each passing, extending the star's suffering and progressively feeding the black hole. Extreme gravity naturally occurs in these strange systems, demonstrating the extremely narrow line between survival and annihilation. To see how delicately balanced the cosmic forces of endurance and destruction may be, picture a star hobbling away from a black hole, its light flickering but still alive. Whole stars can be taken from galaxies by black holes. Although galaxies are teeming with stars, occasionally those stars move. Black holes at the centers of two galaxies can engage in tug-of-war, stealing stars from one another. In some situations, the gravitational power of the other galaxy's core can steal stars from the periphery of galaxies during near approaches. Even stars that have been observed by astronomers to roam between galaxies are probably the victims of such interactions. Black holes and their host galaxies thus function as cosmic robbers, collecting and redistributing starlight over intergalactic space. This massive heist serves as a reminder that galaxies are dynamic, interconnected entities rather than solitary islands. The stars in our night sky are not always faithful to their home galaxies. They are pulled by stronger forces and change their allegiance when gravity compels them to. Black holes can be fed by star clusters that sink into galactic centers. Galaxies change with time. Their structures are continually rearranged by gravity as they change. Over billions of years, dense star clusters circling close to galactic centers may gradually spiral inward. Their stars are ripped apart or devoured by the core black hole as they fall. In this sense, black holes expand by devouring entire star clusters, rather than simply individual stars. These gradual feasts appear to be responsible for a significant portion of the mass of some really enormous black holes. The process also explains why galaxies' cores frequently contain a wealth of old stars that survived these migrations. Imagining an entire cluster descending into darkness illustrates how galaxies use black holes as transformational engines. Despite being damaging, the process shapes the light-shadow balance at galaxies' cores. It is possible to shred stars into gas streams. A star may be destroyed in a tidal disruption event if it approaches a black hole too closely. The stuff of the stars is stretched and drawn into a lengthy, luminous stream rather than being ingested all at once. This stream forms a disk of gas heated to millions of degrees as it slowly spirals inward around the black hole. For months or years, the process can eclipse the host galaxy due to its extreme brightness. From Earth, these occurrences seem like abrupt, intense flares, celestial lights signaling the most extensive damage. Every torn star serves as a warning that gravity has the power to tear even the largest suns apart, thread by thread. These spectral stellar streams, tragic and lovely remnants of undone stars, arc like ribbons across the emptiness. The formation of stars can even be influenced by black holes. Black holes can aid in creation, despite the fact that they are frequently solely considered destroyers. Some black holes release strong energy jets that shoot forth across their galaxies when material falls into them. These jets compress gas clouds, which can occasionally cause the collapse required to create new stars. In this sense, black holes control the rate of stellar birth by acting as both creators and destroyers. Galaxy observations reveal areas with exceptionally active star formation, frequently associated with black hole activity. The life cycles of stars well outside a black hole's direct reach can be shaped by its effect across tens of thousands of light years. The paradox is startling. Spreading new light can be greatly aided by the universe's darkest objects. Around black holes, some stars are trapped in enormous orb-mass long-distance orbits. Near a black hole, not all stars are doomed. Some discover stable orbits that are distant enough to avert destruction while still traveling huge distances held fast by gravity. Astronomers have observed stars such as S2 and S4700 around the super-enormous long-distance black hole at the center of the Milky Way Sagittarius A in our own galaxy. These stars follow graceful ellipses that support Einstein's theory of relativity while they travel at amazing speeds, some exceeding 7,000 kilometers per second. Seeing their orbits is like witnessing the purest form of gravity, stars dancing around an infinitely strong pull. They survive their journeys carved by the deepest wells of space-time, despite living in dangerous neighborhoods. They serve as a reminder that not all stars close to black holes die tragically. Some people spend their entire lives in close proximity to cosmic darkness. Planets can arise from the disks formed by stars. Young stars are frequently encircled by whirling disks of dust and gas. The material that makes up planet seeds gathers together inside these disks, smashing and adhering. Entire planetary systems form over millions of years, shaped by gravity and the central star's influence. We are witnessing the act of creation, enormous creation, as astronomers have taken pictures of these disks with dark voids etched by nascent planets. About 4.5 billion years ago, our own solar system formed in a disk precisely like that. Planets and stars are created together. From the start, their fates were interwoven. A reminder that the planets we walk on and the moons that orbit them are organic byproducts of the process that produces stars. Creation. Studying these disks is like looking into the beginnings of worlds. Bubbles can be formed in the interstellar medium by massive stars. The most massive stars create voids in the surrounding gas and dust by releasing so much radiation and stellar wind. These bubbles, which glow with ionized gas at their borders, can span dozens of light years. The strong radiation inside removes material, leaving the area surrounding the star hollowed out. The bubbles of several big stars can combine to generate enormous superbubbles, which can completely change the shape of a galaxy. These buildings are more than just stunning. By compressing gas at their edges, they affect the development of stars in the following generation. From Earth, they appear as cosmic balloons inflated by enormous breath, incandescent shells in nebulae. Stars, nebulae. They demonstrate how stars actively shape their galaxies, leaving traces of their might carved throughout space, rather than merely existing within them. Dust in the environment causes some stars to flicker. A star's unpredictable dimming and brightening does not necessarily indicate that the star is changing, according to astronomers. Dust orbiting nearby can occasionally be the reason, momentarily obstructing the light when it passes in front. One well-known example is Tabby's star, whose erratic fading confounded astronomers. Debris or dust clouds floating around it could be the cause. These flickers serve as a reminder that the cosmos is not a blank stage, but rather is full with objects that have the ability to block, scatter, or filter starlight. If viewed through the dusty plane of the solar system, our own sun may flicker similarly to those who are far away. As sky watchers, we learned humility from such stars. The distance between us and the light always shapes what we see. The radiation from the brightest stars can form whole nebulae. 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 Entire nebulae glow as a result of hot, big stars ionizing large areas of the surrounding gas with their powerful ultraviolet radiation. For example, the Orion Nebula sparkles because the area is flooded with energy from a cluster of young, massive stars in its center. The gas is pushed back by their radiation, creating holes and forming the tiny light and shadow filaments that we see in telescopic photographs. The very material from which the stars themselves were formed is gradually scattered by this intense radiation, which prevents additional star formation in their immediate vicinity. In this sense, stars are both producers and destroyers, burning away their nurseries while simultaneously igniting them. These luminous sculptures serve as a reminder that light has power and shapes galaxies on a scale of hundreds of light years. Some stars roam the cosmos by themselves. The majority of stars reside in large groups of galaxies that are held together by gravity. Not all, however, remain in one place. Violent occurrences like close contacts with black holes or collisions between galaxies might throw out some stars. Far from any home, these wayward stars float by themselves in the intergalactic abyss. They might be alone for billions of years, moving at hundreds of kilometers per second, without ever nebulae kilometers per second. Coming into contact with another star system, their light traveled unimaginable distances. Despite their loneliness, they act as cosmic messengers, bearing hints about the forces that drove them away. A reminder that even stars can be banished, shining stubbornly against the great quiet of space, is the eerie notion of a lone sun roving through the void between galaxies. The elements within you are continuously being created by stars. Long before you were born, deep within the stars, the atoms that make up your body were formed. Helium is created from hydrogen by fusion. Helium is then converted into heavier elements such as nitrogen, oxygen, and carbon. The process is advanced by massive stars, which create iron, silicon, and other materials. They enhance subsequent generations of stars and planets by dispersing these elements into space after they die. Every carbon molecule in your cells, every iron molecule in your blood, and every oxygen breath you breathe were all once stars. On a cosmic scale, stars are alchemists that transform ordinary gas into the elements necessary for life. You can see your own origin tale inscribed in flaming furnaces billions of kilometers distant when you gaze up at the night sky. In actuality, we are the dust of stars that has been brought into our mind. In space, stars serve as nuclear fusion reactors. Stars are fundamentally enormous fusion engines. The force of gravity causes hydrogen atoms to fuse into helium, releasing energy as heat and light. Scientists aim to duplicate this process, nuclear fusion, as a practically infinite energy source on Earth. For billions of years, a star remains stable due to the equilibrium between fusion pushing outward and gravity pulling inward. Stars would collapse under their own weight in the absence of fusion. With it, they light over unthinkable distances, sustaining planet life and galaxies as they evolve. The direct glow of fusion is what you see when a star twinkles. The universe's raw material is transformed into splendor by atoms combining in a constant fire. The universe itself is a sort of laboratory, as demonstrated by stars, operating on responses that keep us all alive. Hydrogen is converted to helium in stars by fusion. Stars run on hydrogen, the most basic and prevalent element in the universe. Massive pressures in star cores cause hydrogen atoms to collide and fuse into helium, unleashing energy bursts with each reaction. This is the basic mechanism that gives stars their brightness. Helium accumulation alters a star's equilibrium over time, causing it to eventually grow, contract, or transition into different stages of stellar life. Beyond helium, fusion in large stars can produce ever heavier elements. But hydrogen is where it all starts. This silent yet unrelenting change is the direct cause of every sunrise, a series of events that will persist for a very long time after burning for billions of years. Squeezing hydrogen into helium, one fusion at a time, is the source of the universe's light, warmth, and chemistry. The remains of today's stars will form future ones. Although stars pass away, the story does not finish with their passing. Stars add heavier elements to their environs when they supernova or shed their outer layers. Dense clouds are produced when this gas combines with the interstellar medium. New stars are created when gravity gradually brings these clouds back together. With each cycle, stars generate more complex chemistry by carrying on the legacy of their predecessors. The ashes of previous stars gave birth to our Sun, which contains elements formed in prehistoric explosions. The cycle will continue when future stars emerge from the remains of ours. The cosmos is constantly in motion thanks to this cycle of death and rebirth. Stars undergo countless changes as they live, die, and reincarnate, piecing together time. Violent starburst galaxies are where some stars are born. The rate at which stars are formed varies among galaxies. Stars are born 100 times faster in certain so-called starburst galaxies than in the Milky Way due to extremely harsh conditions. These explosions are frequently caused by galaxies colliding with one another, compressing gas clouds into raging waves of star creation. Young, enormous stars burn across entire areas, releasing energy into space. These galaxies reveal the heat of innumerable young suns through their dazzling infrared light. However, the craze is short-lived. The starburst diminishes over a few 100 million years when the gas is consumed or blasted away. What's left is a cosmos that was irrevocably altered by that little bout of chaos. The universe is captured in a moment of astounding productivity as one gloats over a starburst galaxy, an entire cosmic nursery in full swing. Not every star is created equal. Some begin with boys in their dozens. There were probably a lot of siblings around our Sun when he was born. This crowding is considerably more extreme for certain celebrities. Dozens or even hundreds of stars may form in close proximity in stellar nurseries, their orbits being pulled and twisted by their gravitational pull. While some systems eventually have several suns bonded together, others gradually disperse their siblings. Stars can interact dramatically if they are born in a busy neighborhood, taking planets, throwing companions away, or interfering with each other's development. However, as shock waves, radiation, and winds mix materials, the richest chemistry takes place in these same conditions. Imagine the early stages of a star's life as a luminous, cacophonous nursery where dozens of suns erupt alongside one another, competing and working together. For billions of years, certain dead stars continue to shine. White dwarfs are created when stars like the Sun run out of fuel. These star remains are still hot and glow with thermal energy that has been stored, even though they are no longer driven by fusion. They gradually cool over billions of years, becoming progressively fainter. However, the cosmos is still too young for any white dwarf to have completely gone dark because of how many kilometers per second it takes. Much kilometers per second. Much time has passed. Even dead stars still shine, their dim radiance identifying the resting places of once bright suns. Astronomers can determine the ages of star clusters and trace the galaxy's history by observing them. A white dwarf is a star that glows softly long after its fiery youth has ended, offering a glimpse of both persistence and death. Clusters of stars are made up of millions of siblings. Some stars are born in massive clusters rather than in little families. For instance, globular clusters are spherical swarms of stars that include hundreds of thousands to millions of stars. These old clusters, which have remained together for billions of years, orbit galaxies like satellites. Their stars, remnants of a previous cosmic epoch, are some of the oldest in the universe. The night sky would appear unbelievably bright from within, with thousands of suns spanning every horizon. Investigating these clusters provides information about the limits of gravitational binding, galaxy history, and star evolution. They serve as natural laboratories where stars coexist at a remarkable density, demonstrating to us what the most extreme stellar communities might look like. Standing on a planet in such a cluster would be like looking up at a starry sky. When clusters explode, some stars are ejected as runaways. Anarchy prevails in dense star clusters. Stars pull on each other. Additionally, a supernova explosion can significantly upset the gravitational balance. Stars are occasionally hurled forth at incredible speeds by this instability, forming runaway stars that travel across the galaxy. These stars travel lonesome distances from their birthplaces at speeds of up to hundreds of kilometers per second. Their velocity allows astronomers to identify them. They frequently race away from clusters or supernova remnants. The tale of runaway stars is one of explosive beginnings and fateful gravitational dice rolls. They bear the recollection of their origins after being banished from their densely populated homes. Their velocity is much evidence, enduring evidence of the causes that caused them to wander. Our galaxy's central black hole, Sagittarius A, is orbited by a few stars. Sagittarius A, a superlarge black hole around 4 million times the mass of the Sun, is located at the center of the Milky Way. There are stars that orbit it directly, which is unbelievable. For decades, astronomers have monitored these stars as they follow their lengthy orbits around the unseen giant. S2 is one star that approaches the black hole so closely that it whips around it at over 7,000 kilometers per second. Since the starlight bends and redshifts in ways that Einstein's equations predict, observing these orbits offers one of the most convincing pieces of evidence of his general relativity. These stars reside in a dangerous area, yet they persevere, burning boldly as they circle a vast gap of gravity. Observing them is like witnessing the ultimate cosmic ballet, with suns dancing on the brink of night. The orbits of nearby stars can be distorted by black holes. In addition to consuming stars, black holes also distort the surrounding space. Stars that are captured close frequently wind up in odd orbits. While some may spiral inward towards doom, others may slingshot around the black hole at astonishing speeds. The curvature of space-time is still felt by stars at safer distances, and their courses diverge from Newton's predictions. Astronomers have been able to probe the boundaries of physics in a natural laboratory by observing these motions. Without ever having to see it up close, the distorted stellar orbits in the Milky Way's core demonstrate the asterisk Sagittarius A's immense strength. Superhuge black holes that are too faint to be seen otherwise are confirmed to exist in faraway galaxies by stars that are bent into tight swirls. Star warping serves as a signature and a map, the most intense hidden fingerprint of gravity. Beyond the Sun, The closest star is still more than 4 light-years away. The next closest star is unthinkably far away, but our Sun feels familiar and close. About 40 trillion kilometers, or more than 4 light-years, separate Proxima Centauri from Earth as part of the Alpha Centauri system. The trip would take about 80,000 years if a spaceship could travel as quickly as the probe from New Horizons left our solar system. Proxima is our nearest neighbor in the cosmos, though, and it even has at least one planet in its habitable zone. When we look up at the night sky, we see that even our closest star is so far away that it takes years for light to travel across it. The Sun seems less commonplace and more valuable from this angle. Although it is only one star among many, it is the one that keeps our frail existence going. The Milky Way contains hundreds of billions of stars, of which the Sun is only one. Despite dominating our skies, the Sun is just one of the Milky Way's hundreds of billions of stars. Every one of those stars has a backstory. Some are destined for explosive deaths, while others are lonely, partnered, or have planets. Because of their sheer size, there are billions more stars silently burning across the spiral arms of the galaxy for every one we are aware of. Red dwarfs, many of which are smaller, burn faintly for trillions of years. Giants that are thousands of times brighter than our Sun are among them. Even on the darkest nights, we can only see a small portion of them from Earth. When we think of the Milky Way in its entirety, we see a dazzling disk of light so big that our Sun is but one grain in its sweep. Our star is both commonplace and remarkable. Our world is made possible by this common light. The Milky Way contains the majority of the stars that are visible at night. On a clear night, almost all of the stars in the sky are part of our own galaxy. They are the Milky Way's local inhabitants, dispersed across its spiral arms. Only a small number of the brightest light spots, such as those in the Andromeda galaxy, originate from space. From a cosmic perspective, everything else is local, including the Pleiades, the Big Dipper's stars, and Orion's belt. When viewed from dark skies, the Milky Way appears as a luminous strip across the heavens due to its extreme star density, the luminosity of millions of suns combined. The cross-section of a huge, rotating disk of stars is what appears to us to be a personal canopy of sparkling lights. Remembering this makes you feel connected and humbled. The night sky is a window into our galaxy, not a random place. Gravitational collisions have the power to tear stars from their galaxies. Galaxies change with time. Their gravitational pull tugs at everything within them as they collide or pass near each other. After being firmly bound, stars can be launched into intergalactic space. These rogue stars spread their light across the great emptiness as they drift alone, no longer connected to any galaxy. Some might be carrying licenses, orphaned worlds passing through emptiness together. These celestial exiles are capable of traveling for billions of years without ever coming back to their home galaxy. According to observations, intergalactic space is dotted with these roving stars rather than being completely empty. Each serves as a reminder that galaxies are dynamic, living entities, and that, in the correct conditions, gravity's unrelenting pull may break the bonds that keep stars together. Planetary nebulae are marks of cosmic graves left by stars. Like the Sun, stars develop into red giants and lose their outer layers as their lives come to an end. These layers produce luminous shells of gas illuminated by the surviving core as they drift out into space. The end result is a gorgeous formation that has nothing to do with planets, yet is misnamed a planetary nebula. Rather, these nebulae are blazing cemeteries that mark the passing of the stars, cosmic grave markers. Before vanishing into intergalactic dust, they can adorn the sky with delicate colors and shapes for tens of thousands of years. The probable fate of the Sun in billions of years is depicted by well-known examples such as the Ring Nebula and the Helix Nebula. Planetary nebulae ensure that the cycle of creation continues by seeding space with fresh material even as they mark endings. The cooling embers of stars are known as white dwarfs. White dwarfs, which are dense, Earth-sized leftovers that no longer fuse atoms but still burn with residual heat, are created when stars like the Sun die. They are the softly glowing remnants of once living stars that have been smoldering for billions of years. The crushing pressure that keeps them together is demonstrated by the fact that a teaspoon of white dwarf stuff would weigh tons on Earth. Although the universe is too young for any black dwarfs to exist yet, they eventually cool and fade and turn into black dwarfs. White dwarfs are cosmic fossils that hold clues to the galaxy's age and past. To see one is to observe a quiet perseverance as well as a conclusion, the final remnant of a star that was once a brilliant light in the sky. While some stars go peacefully, others do so in violent apocalypses. Not every star has the same destiny. Red dwarfs and other small stars gradually cool into white dwarfs with little show. However, supernovas, which are cataclysmic explosions, frequently kill larger stars. Distributing their outer layers in dazzling light and energy displays throughout space. By creating and dispersing heavy elements, these apocalypses provide galaxies with the building blocks for planets and life. Some of the most bizarre objects in the cosmos are left behind after the most massive stars collapse into black holes or neutron stars. The variety of star life is reflected in the variety of stellar deaths. Every ending, whether peaceful or catastrophic, is a component of the cycle that keeps galaxies changing. A star's death is never just the end in any of these situations. Something new is beginning. We are reminded by stars that the universe is always evolving. The night sky is a representation of both impermanence and permanence. Stars appear to be stationary with constant constellations. But as time passes, stars are created, grow, and die, changing the sky's fabric. Supernova flares are where old stars collapse, and nebula blossoms are where new stars ignite. Galaxies collide, clusters separate, and rogue stars stray into space. Even our sun is transient. It will eventually grow and diminish. Stars serve as a reminder that the universe is dynamic and ever-changing. Each twinkling represents a single moment in a continuous narrative spanning billions of years. To view them is to glimpse flux and eternity. We move along in the infinite rhythm of the cosmos's huge, sluggish heartbeat. I appreciate you coming along on this peaceful trip through the skies with me. We've seen their long, steady lives, their peaceful embers, their explosive deaths, and their flaming births in huge clouds of gas. We discovered reminders along the road that stars are more than simply far-off spots of light. They are the creators of atoms, the architects of everything we know, the timekeepers, and the cosmic storytellers. The idea that your body's bones, blood, and lungs were once formed in the hearts of ancient suns can be a source of humility. In order for you to one day dwell here, breathing peacefully under their light, stars had to live, die, and scatter their ashes. Every night, the sky is more than just a show. It is a record of creation recorded in space. You don't need to remember any of the specifics as we go on from this story. You can allow them to float away like airborne stardust. The sensation, the serene grandeur, the sense of smallness but profound connection is what counts. This universe is made of the same fabric as the stars, and you are a part of it. I would appreciate it if you could like, subscribe, or leave a comment if this post was helpful to you. One drowsy soul at a time, it assists others in finding this channel. You don't need to do anything else right now, though. Simply let your breathing slow. Allow your body to relax and let the day's stress melt away. You may just relax as the galaxies continue to rotate and the stars continue to burn. A star is shining somewhere, but it will take thousands of years for its light to reach Earth. The world will have changed innumerable times, and you will have had 1,000 dreams by the time it comes. The stars serve as a gentle reminder that time is both wide and kind, a current to which we might submit. Allow yourself to float into the silent darkness, propelled by that current. rest in peace. Dream deeply and remember that you have always been filled with the same starlight that shines in the sky. Good night.